Hello, this is a quick video about polar versus non-polar molecules. Just some basics, not lots of detail, just enough to get us familiar with the concept, or maybe remind us of something we've already known. So first, we know that atoms are the smallest individual piece of matter you can find that still has the same characteristic of that. So if you're looking at carbon, an atom of carbon is the smallest piece you can get that still acts kind of like carbon. Same thing for oxygen or gold or whatever other element we're looking at. So atoms are built of two things in the nucleus, neutrons and protons. They are the most massive. Neutrons are neutral, protons have a positive charge, and protons are the numbers that are listed on the periodic table. This is the number of protons. So chromium has 24 protons in its nucleus. That's what makes it that. Carbon has 6 protons. That's what makes it carbon. Electrons are zipping around the outside. In various models, we can have them orbiting or maybe in a probability cloud, depends on what kind of chemical processes you're looking at or physical processes you want to focus on. But they're way on the outside, they're way smaller, and they have a negative charge. Atoms always have a balanced charge, which means same number of protons and electrons. So an atom of carbon would have 6 protons and therefore 6 electrons. An ion has an unbalanced charge, has a charge that could be positive or negative. So we have a cation, which has a positive charge, or we have an anion with a negative charge. So if there are fewer electrons than protons, say 5 electrons and 6 protons, that would be a positive ion, a cation. Or negatively, if we had, and don't worry about if these are real or not, just if they had 8 electrons around a 6 proton nucleus, we would have an anion, a negatively charged ion. For those electrons that are around the outside, there are different shells or orbitals, and these go in order, and we count by how many are in a row. So there are 2 in this row, 1, 2, 3, 4, 5, 6, 7, 8 in this row, 8 in the next row as well. And then below that, things get a little bit weirder, and we're not going to worry about it in biology. But the first 3 shells go 2, 8, and 8. So if you have a nucleus, there's 2 electrons that fit in here. And then in the next shell, bumps up to fill up to 8. And then the next shell fills up to 8 again. Again, there are lots of models of how this could look and shapes that it could take in geometry and stuff. But for now, 2, 8, and 8 is all we need to remember. So valence electrons are electrons that are on the outermost shell, or we can call it an orbital, the outermost level. So we don't worry about the ones that are on the inside. Those aren't accessible. And whenever we're making a bond, whether it's ionic or molecular bond, we want to have a full valence shell, which means that you want to have a valence shell like our noble gases. Our noble gases here, helium has 2 electrons. An atom of helium has 2 electrons. That's happy. Neon has 2 plus 8. So that one's full and that one's full. That's again happy. The next time we get full again is 2 plus 8, which is 18. And that's argon, the next noble gas. These things are unreactive. The noble gases are unreactive because they already have their happy number of electrons in their valence shell. So if we look at something like water, water has 8 protons. Sorry, oxygen. Water is H2O. The oxygen part of water has 8 protons. We can look back here. Oxygen is atomic number 8. That's 8 protons. And therefore, it comes with 8 electrons. An atom of oxygen will. 1, 2, 3, 4, 5, 6, 7, 8. So oxygen has 8. But a full shell, 2 plus 8, would be 10. So it's missing 2. If it had 2 more, then this outer shell would be full. And in this picture, it's already full because this is an already built water molecule. Hydrogen is atomic number 1. It's 1 proton and 1 electron. And the first valence shell is 2. Remember, it was 2, 8, 8. So the first valence shell is 2. So to get up to 2 from 1, it's missing 1 electron. So hydrogen has 1 and 1. It wants another 1. In order to make a happy, stable molecule, hydrogen and oxygen can try to fill up their valence shells. This is kind of a basic chemistry principle. We're trying to fill up those valence shells. So oxygen is missing 2, and it wants to steal these 2 from 2 hydrogens that are nearby. And it tries to. But hydrogen also wants to steal 1 from oxygen. And neither one of them are going to win this fight, largely because hydrogen is so light. It's like if you tried to pick up something that was attached with tape or glue to a very light object, the whole thing is going to come along. So you try to steal this electron, oxygen tries to pull that in, but this little proton comes along for the ride too, because this is 16 times heavier. Has a much bigger, stronger pull. But this works out pretty well, because from hydrogen's point of view, it thinks, hey, I've got 2 electrons in my valence shell. From this hydrogen's point of view, again, it thinks, hey, I've got 2, that's good, I'm happy, I'm happy. And from oxygen's point of view, it thinks I've got 2, 4, 6, 8. Again, that's a great number to have in your valence shell. All 3 of these components think that they're satisfied, and neither one of them wants to let go of any electrons. This is what we call a co means together, valent bond. Valence are talking about the valence electrons. They're sharing those valence electrons because they both want them, and they're never going to let go. Well, not never, never, but never in normal circumstances. So this covalent bond is interesting because if we look at water, this is the same thing. This is oxygen and hydrogen. This is water again, but only focusing on these electrons that they're sharing. If we look at this molecule from the point of view of a tiny, tiny, tiny little thing coming in, if you were coming in from this point of view, what would you see first? You would see all of these electrons here. You would see a negative charge. If you were coming in from this point of view, what would you see first? The first thing you would see, the first thing you're closest to, are positive charges. So from the point of view of something looking at these molecules, it has a negative region and a positive region, even though the overall molecule is a molecule. It's neutral. So we call this a polar molecule because we have a positive pole and a negative pole. The positive pole way up here, the negative, or positive pole way down there, and the negative pole way up here. Not all molecules do this, but some do. Polar molecules are really good at dissolving other polar molecules. They're really good at working together because, as you imagine, if something has a positive and negative side, then something else with a positive and negative side will just align itself like this so the negatives and positives can come together. Or maybe like this so the negative and positive can come together. Because positive and negative like to be close to each other. So positives and negatives can be close, no matter which way we're looking, they're close together. Polar molecules are really good at dissolving other polar ones, and same thing for nonpolar. So things like lipids are nonpolar, things like water, that's polar. And different types of bonds you might remember about too. We're describing right now a polar covalent bond like water. A nonpolar covalent bond happens a lot. And for nonpolar things, we're just going to broadly list the category of things we might expect them in Unit 1, which are lipids, oils, and fats. They don't have a positive region and a negative region. It's just all kind of neutral. And the other type of bond is an ionic bond, which is where one of these initial reactants has one too many electrons, and the other one has one too few. So the classic example of this is sodium chloride. If we look back up at our periodic table, sodium has 1 extra, it has 11. 10 is good, 11, so that means 1 too many electrons. It wants to get rid of an electron. And chloride is missing 1. It's at 17. It needs 18 to be happy at a full valence shell. So if sodium can just toss an electron over to chloride, it will, and chloride will keep it and become an anion. And sodium has lost an electron, become a cation, and both of them are more happy. And this bond is very weak in water. In biology, everything is happening in water because water is polar, and all those positive and negative bits can get torn apart or dissolved pretty easily. So hopefully this is a quick reminder of something you may already have known.